All right, so last chapter, chapter 10. You there, Fred?
I'm here.
All right, so we're going to look more at structure of compounds, specifically molecular compounds in this chapter. All right, we can draw Lewis dot structures now, and from those Lewis dot structures, we want to be able to predict information about relative boiling point, melting point, reactivity. All right, so to do that, we need to know what the Lewis dot structure is telling us about the shape of the compound. Okay, when I see a compound like this, CH4, I need to know what shape it is. Or when I see the Lewis dot structure for something like water, I need to know its shape. I can draw it like this or like that, right? But which way is it really, and what is its shape? All right, so that's what we're going to work on. Remember, we're in a three-dimensional world, but we're always drawing on a two-dimensional surface, okay? So that creates some things that we have to always be mindful of. So, for example, nitrogen here has 1, 2, 3, 4 regions of electron density around it, right? Our central atom has 1, 2, 3, 4 regions of electron density around it. Identifying the number of regions of electron density is the first step in knowing the structure, the shape of the molecule, of a molecule. All right. So, Fred, how many regions of electron density are around this oxygen? How many electron domains, call them?
Do you count lone pairs?
That's right. Each lone pair is 1, so there's 2 there.
And then bonds?
Each bond, whether it's a double bond or a triple bond or a single bond, counts as a single region.
Oh, so that's 4 there.
That's right, 4. Just like this one, we have 4. How about this one down here?
4 regions there.
Very good. How about this one?
5 regions.
That's right. 1, 2, 3, 4, and 5. How about the carbon down here?
Is that just 2? You said the double bonds counted as 1?
That's right. So around the central atom, that's all we're caring about right now, 2 regions of electron density. Very good. So identifying the number of regions of electron domains, we can call them a bonding domain or a non-bonding domain, or just regions of electron density is another way to think about it. Now, the shape depends on these number of domains because those domains try to spread out as far as they can. All right? They try to get as far away from each other as they can, and this is called the VSEPR diagram, or the valence shell electron pair repulsion theory. The VSEPR theory is basically saying that all of your surrounding, all of your atoms on the outside of the central atom, whether they're bonding atoms or non-bonding regions of electron density, try to get as far away from each other as they can. All right? So if I have one central atom and 2 regions of electron density that are, in this case, bonding, we would say that the molecule's shape is linear. All right? Can you see why we call it linear?
Yeah, it looks like a line.
Okay. If I have one central atom with 3 bonding regions around it, our shape is trigonal planar. Trigonal because it's like it's a triangle, but planar because they're in the same plane. All right. Now, excuse me. Is it intuitive to you that this angle would be 120 degrees?
You mean, should I already know that?
Yeah, did you already know that this would be 120 here?
No.
Did you already know this was 180?
Yeah, I know that.
Okay, so you know that all the way around. If I were to go all the way around, how many degrees is that?
Well, that's 360.
That's good. Remember the football team that said, we're going to turn this thing around 360 degrees.
Oh, what's that mean?
Well, it's a joke because if you turn it around 360 degrees, you're going exactly the same direction as you started with.
Oh, yeah. Did that really happen?
It did. Football personality said at one point, I'm going to turn this football team around 360 degrees. Okay, so 180 degrees is what you want to say if you're a sports enthusiast and you want your team to go the opposite direction of what they're doing. If they're losing, you want them to win, right? But if you take the 360 degrees and divide it into 3 parts, that's where you get the 120. So hopefully the 120 can be intuitive to you now. 3 regions of that circle. Circle split by just 3 regions, right? It gives us an angle of 120, and the shape is what we call a trigonal plane, or trigonal planar. It's trigonal, but it's all in the same plane, all right? So this shape here is not intuitive to us in terms of the angle, but we need to remember this number. It's 109.5. And it turns out that if you take a central atom and put 4 regions of bonding, 4 bonding regions on it, then you get this shape, this trigonal or tetrahedral shape. Okay, so I'm going to introduce you to a little website here. It's called MolView, and it's just a little free little website, and essentially what it's doing for us is it's allowing us to visualize the compounds. So here's its web address if you want to go to it and practice. But I can draw my compound, so I can make this compound a carbon, for example. And I can put 4 hydrogens on it like that. And then I can clean up my structure, and it'll kind of make this structure the way it should look. It doesn't show the hard hydrogens there. And there I can see my compound that I've drawn. All right. Now, we're not used to seeing, I mean, we can kind of intuitively think about what the angle would be if we had a central atom, right? So let me get these up out of the way a little bit. What the angle is when we have a central atom and 2 bonding regions, right? We can say, oh yeah, 180 degrees there, right? We can also kind of intuitively do that if we have 3 bonding regions now, because we were reminded, 120 degrees. But when we have 4 bonding regions and we're working on a 2-dimensional surface like this, it's hard to visualize and know exactly what's going on. So here we have 4 bonding regions, and the angle is 109.5, and that's a number we kind of just have to memorize moving on, because if I wanted to draw this, I would be tempted to draw it like this, right? And say that the angle looks like it's 90 degrees, all right? But that's not the case, because I don't draw it in 3 dimensions on my piece of paper. Now I can try to draw it in 3 dimensions. I can try to make it look like this bond is coming out towards me, and maybe one's coming up there and one's in the plane, and then there's one in the back maybe that is going out of the plane. Not a very good drawing. Trying to draw something like this. Let's see here. Right about there, right? I was trying to draw something like that. Anyway, this you can kind of see would make a little triangle on the bottom, and then a pyramid maybe like that. But they call this shape tetrahedral, and it's referring to tetra, 4 sides of 4 sides that this shape would have. One side would be right here. One side would be right there. That's the second side. If it were a die, for example, you were to roll it like a dice. And then the third side would be on the back side of here, and the fourth side would be on the bottom. All right, so that's our tetrahedral shape. And the angle, which again, even if we could draw it really well, the angle wouldn't be very intuitive to us, so we do have to memorize it. It's 109.5. If I have 5 regions of electron density, all right, then I have 3 that are kind of in, and I'll make one of these for us. So a good example is phosphorus pentachloride. If we look at this molecule here, phosphorus in the middle, 5 chlorines on the outside, the regions, there's 5 bonding regions, we say. The one on top and the one on bottom are 180 degrees from each other. If you move the one on the top and the bottom right in line like that, you see that there is this 120 degrees from each other, the ones on the sides, and we call the ones on the top and the bottom polar, axial. They are on the axis, if you were to think about this thing as a globe. And these three around the outside are called equatorial. So we have axial positions and equatorial positions when we bind 5 regions bonding to a central atom. Okay? And we call this shape trigonal bipyramidal because it's like this. These three form the base of a triangular pyramid on top, and the three also form the base for a triangular pyramid on the bottom. Okay? So we have to remember that there are equatorial and axial positions. Equatorial are the ones along the middle, and our axial ones are up and down. Axial, again, are 180 degrees from each other, 90 degrees from their neighbors on the equatorial, their equatorial neighbors. And the equatorial atoms are all 120 degrees from their equatorial neighbors and 90 degrees from their those axial neighbors. Okay, so if I have 6 regions of electron density around a central atom, the resulting shape is what we call octahedral. So if we look at an example of a central atom with 6 regions of electron density that are binding, 6 bonding regions around it, we get this shape. This shape is called octahedral because it has 8 sides to it. Again, if it were to be kind of turned into a dice or a die, right? 8 sides. Notice that it's basically, we don't really refer to axial and equatorial positions in an octahedral compound because all of them are the same if it's the same elements being bound, right? All of them are the same in terms of their proximity to their neighbors and the space that they have. If we look back at our trigonal bipyramidal, axial ligands, axial bonding spaces, have a little more space. Sorry, equatorial regions have a little more space than the axial.